everybody, and here we are in the E1 mechanism and part 3 of the Organic Chemistry 1 Eliminations chapter. And we'll now, with the E1, the basic E1 mechanism is shown here at the top of the page, and in it, just like in the SN1, we have to form a cation, and once we form the cation, then in the rate determining step, then we can pull off a hydrogen to form the carbon-carbon double bond. So the stability of the intermediate, the cation, plays a large impact in how fast the reaction will be. The most reactive alkyl leaving groups are the tertiary ones, with the least reactive, the primary, in an E1 mechanism. And this is all because of the stability of the intermediate cation. We learned a long time ago in chapter 4 and the stability of alkanes, that the tertiary cation is most stable, then the secondary and the primary won't form very easily at all. So the tertiary cation is the most stable, therefore it's the easiest to form, which makes the tertiary leaving group the most reactive for this reaction. So in this reaction we have, or in an SN1 and an E1, they both have the identical starting steps. They have to get to the cation, and from the cation we can either remove a hydrogen off of the adjacent carbon to the cation with a base to get to the elimination product, or a weak nucleophile can add in the cation to form our substitution product. We've already talked about substitution reactions a bunch, and we'll go through elimination reactions now for a while. In the reaction at the bottom of the page, we see the E1 mechanism proceeds similar to the E2 mechanism and prefers the more substituted product if it can get there. So when we think about what has to happen in the mechanism, if we do not have a good leaving group, we have to make a good leaving group. So here we have the strong acid and heat, so we protonate the alcohol to make a good leaving group. It leaves, forming the cation, and then we can remove either of the hydrogens, either one off of one of the methyls or one off of the CH2 next to it. So to get to the more substituted alkene, we need to take a hydrogen off of the more substituted carbon to form the major product. For getting to the other one, we would take a hydrogen off of the less substituted one to get to the less substituted product and the less preferred one. So here on this top of this page, we have a reaction predict the products for the following E1 mechanism. And since from what we said already, we need to first think about where do we have beta carbons that have hydrogens. So these are the large ones. We have the two CH2s and then the CH3. Is there any symmetry in the molecule is the second thing we need to think about. And we have the two CH2s, they're exactly the same, so either one of those would form the same product. And then the CH3 hydrogens are equivalent, so they would all, either any one of those three would form the product at the bottom. So how are we going to decide what can happen in the reaction, since there are two different products possible to form? So we need to think about what kind of stability the alkenes are, and the one, if we go with the double bond out to the CH3, we get a di-substituted alkene. If we go to one of the CH2s, and it doesn't matter which one because, as we said on the last page, they are equivalent, we get a tri-substituted alkene here, and we've already talked about the more substituted it is, the more stable the alkene is. So our major product would be the one that is more substituted. When you have the possibility of a cis versus trans alkene forming in an elimination reaction, as it shows here, that the trans alkene is going to be the favored one over the cis alkene. So, and that's just how things are, and we'll talk more about that as we go on in this section. So, drawing the complete mechanism for an E1 mechanism, the first thing that has to happen, if you have a good leaving group, the leaving group will leave, forming the cation, and then we pull off the hydrogen with our weak base to form our product. So in this first one, there's only two steps when we add water and heat to the T-butyl chloride, since we have the good leaving group to start with. If we didn't have a good leaving group in the second reaction here on this page, we have to take our alcohol, T-butanol, protonate it to form the protonated T-butyl alcohol, which then has a good leaving group on it. The leaving group can leave, forming the cation, and then our water can go grab the hydrogen to form the alkene. So in this one, there are 3 steps in our mechanism, whereas the first one only has 2 steps, because in the first one we have a good leaving group, and the second one we have to make a good leaving group to get the reaction to occur. Now, the next thing we have to be careful of is if the leaving group leaves, like in this example, forming the cation, if that cation is not the most stable cation that can form, the reaction will rearrange, because here we have a secondary cation, and here we have a carbon that's quaternary, that if one of the methyls migrates over, we would form a tertiary cation. And we all know tertiary cations are much more stable than secondary cations. Since the tertiary cation is much more stable than the secondary cation, that rearrangement will occur, and there's no going backwards in it. And then we can remove the hydrogen to form our alkene, and we get a more substituted alkene than what would have happened had it not rearranged. And it's all because of the stability of the cation going from a secondary to a tertiary. And you have to be careful as you're looking at reactions. Can it rearrange in the reaction? And make sure you spot when it can rearrange. And for class, with where we are, I won't make you decide what's going to rearrange. It'll always be 3 of the same thing, or it'll be a hydrogen that migrates. So here we have 3 methyls. One of the methyls migrates. It could be 3 phenols, 3 ethyls, whatever, but it'll always be 3 of the same, just to make sure we understand what's going on. So here we have a reaction where we don't have a good leaving group in the beginning, so we have to add the strong acid to protonate it to make it a good leaving group. It can leave, forming the cation. It's a secondary cation again, so since it's next to that quaternary carbon, one of the methyls migrates over to form a tertiary cation, and then we remove the hydrogen to give us our alkene. So we have to be sure we recognize that as we're working problems, do we have a good leaving group or not? If we don't have a good leaving group, the first step has to be making it a better leaving group. In this, we're adding the strong acid to protonate the alcohol. So here we have at the top of the page the elimination reaction we talked about on the previous page, in that the major product would be where we form the most stable alkene, but it is not the only product for the reaction, and that is because the stability of the alkene, the stability of the radical, and what happens during the reaction, there are 3 possibilities. The first 2 are formed after the rearrangement occurs. The third one forms before the rearrangement occurs. and that's why it's only formed in a very small amount. And on the next page, what we're going to do is draw the mechanism for the formation of all three products so we can see what happens. And then we'll come back and talk about the E2 reaction, which we've already drawn the mechanism for. The mechanism happens all in one step, where the base comes in, grabs the hydrogen, forms a double bond, kicks off the leaving group. All we need to do is show 3 double-headed arrows required for the overall mechanism. So here we have the mechanism for forming all 3 of the products, the major one, the tetrasubstituted alkene, the disubstituted alkene after the rearrangement, and then the monosubstituted alkene that happens before the rearrangement occurs. So for all 3 of them, the first thing we have to do is protonate our alcohol to make it a good leaving group. Then it leaves, and this happens for all 3 compounds. There is no change in the first 2 steps of the mechanism for both of them. We have to get to the cation, and then from the cation we can actually, let's go ahead and redraw the same cation 3 times. So we can show the formation of all 3 products. So we have that cation, we've drawn it 3 times. Now to get to the least substituted alkene, it happens from this cation before the rearrangement occurs, and so all that happens is we grab a hydrogen off of the end and we get to that least stable alkene, least substituted alkene. Now I shouldn't have drawn that one 3 times. Let's go back one. So from that cation we can have the rearrangement occur where the methyl group migrates over to form the most stable alkyl cation that we can. We can redraw this cation, and it'll be easy to get to the other 2 products from it. So that's just the same cation drawn twice, so we keep track of what we have. And then to get to the 33% product, what happens is the water would come in, grab the hydrogen off of the methyl, forming the double bond, and that gets us to this positive charge, or this alkene. And then the other reaction, the water, as we showed in the last page, the water comes, grabs the most substituted hydrogen, and we get this product. This one is the most stable alkene because it's tetrasubstituted, so it forms the most, 64%. Then this one is next. It's a disubstituted alkene. It forms in 33%. And then this one, the least substituted, forms in only 3% of the product that is formed. So these are the 3 possible products from it, and you should be able to draw the mechanism for the formation of all 3.